So this consists of the idea is to realign the data with the clock and detect the phase difference between the original data and the retime data. Also, you would like the phase detector output to be 0 when the clock is in the middle of data. So you also generate a half period pulse in exactly the same way you generate the phase difference signal, and use these as up and down. Okay. And these up and down signals go to a charge pump. Okay, and these go to a VCO. The VCO output is fed back as the clock. Okay. And this is the data, and the recovered data comes out of here. Okay, and this itself is the recovered clock. That is the output of the VCO. You can also take the data from this flip-flop, of course, the first one. Okay, this is okay. So this works in exactly the same way as the PLL, and all the equations remain the same, except that because you don't have transitions in every cycle, you also have a multiplying factor of the density factor in the phase detector gain. Okay, whatever expressions you had for the other one works, except the whole loop gain is multiplied by the transition density factor. Okay. So density factor is defined so that for alternating data, for 1010 data, the density factor is 1. That is, in every bit transition, there is a transition. In every period, there is a transition. And in random data, obviously, that's not the case. So if you have purely uncorrelated random data, then the density factor will be half. Okay. So either bit is 1 or 0. It's the same as saying either you can have a transition or you don't need to have, you can have a case with no transition. Okay. So behavior looks like, if this is the phase of the data, this is the phase of the clock, we can also draw this model in the phase domain to see how it behaves, right? So the VCO model remains the same as before. It's an integrator. KVCO is the VCO gain in hertz per volt. Okay, between its control voltage and thus you get an integration. Phi VCO is the same as phi clock, and you measure the error between phi data and phi clock and feed it to two paths. Firstly, in the model you need to have multiplying factor, which is the transition density, and you have two paths, integrating and proportional path, which are added together. Okay. This will be the kind of incremental model in steady state. And also in steady state you have an error signal E of t added to this. What is E? It's a square wave with 50% duty cycle. Okay. It is, I mean, when it reaches steady state, up will be active for half a cycle and down will be active for the other half cycle. So E of t is a plus minus 1 signal. Okay. So there will be steady state phase disturbances in the recovered clock. Now this can be, the phase disturbance can be controlled by controlling the bandwidth of the phase lock loop. Okay. By placing the poles and zeros appropriately. And also, I don't have space to show that, but as usual I can have additional poles. In fact, the existence of this capacitor implies one additional pole. If I want to attenuate that jitter further, I can have additional poles in the loop filter. Any questions on this? And how do you make this phase detector? I think you already have all the circuit design experience to make this. You have made the flip-flops in the first assignment and you also know how to make the XOR gate. Again, you can all choose any architecture, but here we have been talking about high-speed equalizers. That's the, in that case you will use CML circuits for the XOR gates as well as the latches. But of course it will work even if you don't use CML. I mean, you realize this logic using any other type of realization, it will work. Okay. Now if the transition density is very low, then what happens? What will be the up and down signals? Let's say when there are no transitions, what is up and what is down? Huh? Down always remains? Does it? Both will be 0, right? I mean, if there are no transitions, the data here is constant. So you get an unchanging data here. So data in the delayed version of the data is the same as the data itself. So you will get 0. So that means that essentially the loop, the VCO is not getting any correction, right? So it is as though you break the loop at this point. So the VCO will run open loop, and because the VCO frequency will not be exactly the same as the input frequency. So even if you assume, I am not talking about VCO drift and so on here. Just because of steady state disturbances, when you apply the correction, on average the VCO frequency will be the same as data frequency. But at the moment the transition cease to exist, it may not be exactly the same. So after a while the phase of the VCO will drift away from the correct one that is required. Okay. So in any CTR there is a limit on the number of consecutive identical digits that can be tolerated. And the way to estimate that is, you can imagine, you can calculate the steady state variation in the control voltage. Let's say this is the average frequency, and you take the maximum deviation from that. Okay. At that maximum deviation, you see how many symbols it takes for the VCO clock to drift by a certain amount, by half a period. Okay, that will give you the CID. But that's not the only reason, that's the general idea. So the disturbances may come because of steady state disturbances on this, or maybe, for instance, we assume that this capacitor holds charge. So in some architectures, in some cases, the capacitor may have a leakage, or maybe there is some other part of the circuit that has leakage. Okay. So no capacitor will hold its charge indefinitely on a chip, right, because there will be leakage paths. So that can be modeled by something like this. This current may be of the order of nanoamps or whatever it is. So there also, what happens in this case, the voltage will keep in steadily decreasing. Okay. So in that case, the actual value is supposed to be here, but then it starts drifting, and you can again see how long it takes for the phase error to accumulate to a certain extent. Okay. So you know the gain of the VCO. So you know the relationship between the control voltage and the VCO output. So from that you can figure out how long it takes for it to drift. Okay. Any questions? Has any of you made the phase detector and simulated it? The deadline is still like so many days away. Okay, so this is one type of phase detector, and there are variants of this. There are, so for instance, you get these, the up and down will give you error waveforms, right? To minimize that, there are other kinds of architectures which will reduce the amount of error, basically reducing the amount of jitter. So as I mentioned yesterday, one of the papers that I suggested by Lee and Bulza-Kelly is about modifying this phase detector to get a better phase detector. Okay. There are lots of architectures. Once you understand the general idea, you can take some existing ones and modify it, or you can start from scratch and try to figure out how to find out the difference between the data and clock phases. Now, once you come up with a phase detector architecture, then you have to simulate it, or at least calculate it and see what is the jitter performance of it, what the bandwidth will be with that, what the phase detector gain is, and so on. What are the conditions under which it doesn't work, etc., etc. Okay. How did we calculate? Oh, okay. So the phase of the VCO is okay. Now let's say 0 is the time at which you start this. Okay, at time 0 the phase is the correct one, and you want to see how long it takes for it to drift, right? Sorry, you want to find this T max, at which point it becomes equal to, in this particular case, so this is one data period. Okay. So we say that this edge can be here, but if it goes and crosses this period, it's no longer useful. Of course, in reality, it should be some fraction of this. Okay, you can't let it drift all the way to the edge of the data period. But let's say it is this, so you have to solve this equation. Okay, so now it could be that this control voltage is in error by a certain amount. Okay, so this is the, actually what you want is the excess phase, right? So let me rewrite this. The total phase of the VCO is 2 pi f naught t, this is due to the free running frequency, plus 2 pi k VCO times, so this DCV control is what I call the DC value to get the right frequency. Okay, maybe you are not operating at the free running frequency, you are operating at some other frequency, then you need to apply a DC to this. Now, if this is all there is, then the VCO frequency is exact. The VCO frequency is f naught plus k VCO times V control times DC. Okay, but in addition to this, there will be some error. So, like I mentioned, in this case, the center line is the VCTL DC, but when the transition stop, it may be above or below the center line. Okay, the deviation away from that average value I call So let's say delta VCTL. Okay. Now what I am concerned is that they should not cross pi or minus pi. Okay. So I want the absolute value of this to be smaller than pi. Now delta VCTL can be a constant. This is like the loop. I mean, in the loop, V control is slightly above the average value, and then you break the loop, and then you see how long it stays locked, meaning how long the clock stays within the data interval without going out of the data interval. Okay. So in that case, you can figure out easily. It is 2 pi kVCO times delta VCTL times T max. Okay. This should be less than pi. Now, in case of leakage, what happens is you have a capacitor and you have a leakage current. Okay. So let's say you start off with the right value of the control voltage so that it is operating at the free running frequency, but then it starts leaking. Now if the loop is closed, the closed loop will take care of this. Okay. The negative feedback loop will compensate for whatever current is going out of this. So if there is a leakage current, what happens? What happens is this up and down will contribute some currents such that on average the leakage current is compensated. So there will be a phase offset because of this leakage, but it will be compensated for. Okay. Now if you break this loop, the voltage will constantly go away from the value that is required. So then again you can figure out it is 2 pi, you will get some, this is, what is the V control in that case? That is the leakage current divided by C. That itself is times T, okay, times dt. So you will get some square function of T max, and you can calculate the leakage. I mean calculate T max such that the phase drift is less than a certain fixed value. Okay. So in any other case of any other error, you do the same thing. And this is the idea that if you have a time varying delta V control, you want to calculate the amount of phase deviations, that is the phase jitter, you again use the same formula, that's all. So you have this sort of desired phase, right? The ideal phase of the oscillator is 2 pi times the frequency of the oscillator times time. Whatever is in excess of it is the phase jitter or phase error. Okay, that you calculate by putting the appropriate value in the control voltage. Okay. So that's how we calculated also the spurious response when we did the analysis of the frequency synthesizer, right? So you have some, in response to a square wave, the control voltage changes by some extent, and that goes into the VCO. And so basically, essentially, what we calculated was this. We did it in a slightly different way, but that's essentially what we did. Okay. Yeah. Yeah, that's correct. So basically, no, I mean you somehow implying two cases. There is only one case, right? When there are no transitions, it will start drifting away. Now, when it drifts by, let's say, pi by 10, it may still be okay as long as the transition occurs before that. You're fine. Okay. Yeah. Yeah. Yeah, that's correct. So that is why, like, the data should be such that the number of consecutive identical digits is limited to some value. Okay. Yeah, that's correct. Yeah, there will be a constraint on the data. That's correct. So if you have random data, let's say so the transition probability is half, right? So let's say you design a PLL, design this clock and data recovery circuit so that it tolerates 100 consecutive identical digits. What is the probability that it will actually drift away beyond that? Huh? 2 to the minus 100, right? So this is a very small probability. I mean, this always exists, but you can neglect this. This is, what is this? This is 10 to the minus 30, right? So this is, I mean, this is something very small. You don't have to worry about it. No, I mean, you can just make this robust enough, right? Yeah. No, so I have not actually said how much the drift will be, but in practice I can tell you that, okay, it's not so difficult to make it not drift for some, let's say 100 digits or something. Now this also, actually some of these things depend also on the absolute value of the frequency, right? Now, when you are operating at high frequencies, when you are operating at 10 gigabits per second, each bit is 100 picoseconds. So 100 bits is only 10 nanoseconds, right? So it's not that long a time. So there, when it's only 10 nanoseconds, leakage is not a big issue, okay? But then, let's say you are operating at megahertz, 1 megahertz, then like 100 symbols is how much? 10 microseconds. Sorry, 100 microseconds. So 100 microseconds is a long time, okay? So there, actually the leakage current can be a problem. So it depends on a lot of other variables. So there is leakage current and there are other errors that can be injected and so on. But typically it's not so difficult to arrange it so that you can guarantee, let's say, one transition every 25 bits or 50 bits or something like that, okay? Now if you say that the data is purely random, then clearly there is a probability that you will have 100 or more than 100 consecutive identical digits. But the probability of that is small enough. Now if you are talking about, let's say, bit error rates of 10 to the minus 15 and so on. So this kind of probability of PLL's drift, you would ignore it. I mean, this is not the issue that is limiting the system, right? It's something else. But I mean, it's not that you add some other block and make it more robust. If the PLL is if the VCO is stable, it doesn't have any temperature drift, it will do it. But this is a more fundamental problem. If when you have no transitions, you can't measure phase, okay? So you do all of the other, you take care of all of the practical issues, like you minimize leakage, you minimize the other sources of error in the V control, you don't want any noise coming into V control, you minimize all of that. But there will be some limitations simply because if you don't have any transitions, you can't meaningfully measure the phase. Yeah. Yeah, it is a bit error. I mean, not for that bit, for many more bits until it gets corrected again. What is the? Yeah, that's correct. It will be a bit error. So that's what I'm saying. So let's say the probability, it can tolerate 100 consecutive identical digits. Okay. Now, when you have normal random data with a transition density of half, the probability of actually crossing over pi is so small that this doesn't contribute anything to the bit error rate. Okay. So if there are no other errors, then there is a probability of 10 to the minus 30 that you will have you will have the clock in the wrong place and so on. So the resulting bit error will be of the order of 10 to the minus 30 or thereabouts. Okay. All I'm saying is if you design it for a long enough string of consecutive identical digits, the bit error rate because of this will be so small that you would not be worried about this. Okay. So yeah, that's what it does. Eventually, I mean, you can evaluate the bit errors based on how far it drifts and how it corrects back. Okay. Is that okay, or I don't know if that's what you asked. Yeah. Anything else? Yeah. Yeah, that's right. Well, to some extent, right? So there is a raw bit error rate, that is, you send these bits and you see how the bits differ. Now there can be coding and other things in it which will let you correct it even if there is some raw bit error rate. That is, the net bit error rate is much better than the raw bit error rate. Okay. So in a real communication link, what happens is you, for every set of bits, let's say for every 8 bits, you probably send 10 or something. I mean, something more that has all kinds of information on what the bit is, where the frame starts, where something else happens, and so on. So some errors can be tolerated, but here we will let's only concentrate on raw bit errors of some degree. Okay. So the bit error we get from the Q function, Q of the signal to noise ratio, that is the raw bit error rate. If you see the bits that are transmitted here and the bits that are transmitted there, how much will they differ? Now they can differ by let's say 1 part in 10 to the minus 9, but then you can have additional coding that will make sure that the error in the total information bits that you are sending is maybe 10 to the minus 15 or something. Okay. By adding redundancy, you can do all of that. Anything else? Yes. The other day we started evaluating the transfer functions inside a PLL from different sources to the output. We will just complete that exercise now. And the exact same calculation will hold for the linear phase detector with data. Okay, the block diagram is the same, so anything you evaluate here is the same. Only difference in the block diagram is this n is 1 in case of the clock and data recovery circuit typically. The VCO will be at the same frequency as the data. There won't be any division in the feedback. Okay, so what is the loop gain of this? It's quite simple. It's okay, and we'll assume that it is well designed. So in fact, I'll also add another pole. At a frequency P3 radians per second. Okay. So it is well designed, meaning if you plot the loop gain magnitude, it looks like this. Okay. And what is the frequency at which it crosses unity? Two pi kpd kVCO by n. Okay, this is omega, and this is the magnitude of the loop gain. So what is the input here can be the reference phase, the phase error in the reference, or it could be any other error that is added because of whatever reason. Okay, it could be error because at the divider output and so on. So what is the transfer function phi VCO by phi ref in terms of the loop gain L? L by 1 plus L. That's it. Into n. So this is what this is, right? So in general, in a feedback system, you have the ideal gain times L over 1 plus L to be the transfer function. The ideal gain is the gain when the loop gain is infinity. Okay. Now we can make some, just to graphically evaluate the gain, we can make some approximations. Now this is approximately n in the range where the magnitude of loop gain is much more than 1, and it's approximately equal to n times L when the magnitude is much less than 1. Okay. In the first case, I neglect 1 compared to L. In the second case, I neglect L compared to 1. Okay. So with this, essentially it follows the loop gain itself when the loop gain is very small. It follows the feedback factor when the loop gain is very large. Okay. So this is a simple way of, if you plot the loop gain, then you can plot the closed loop gain in a pretty simple way. So this is L, magnitude of L. What is L over 1 plus L here? If I wanted to sketch L over 1 plus L, what would I do? Yeah. So there is a unity gain frequency. That is why the unity gain frequency in a feedback loop gain is significant, right? This is one of the reasons. So L over 1 plus L will be this. Okay. It also tells you that any poles in the loop gain that you have beyond the unity gain frequency will appear just like that in the closed loop transfer function also. Okay. So what happens here? In the loop gain there is a 0. In L over 1 plus L there is nothing. Let me perhaps rephrase it. Let's say I have two systems with different loop gains. One of the loop gains is this. The other loop gain is this. Okay. Both have 20 dB per decade slope when they cross 0. I mean, they are identical after that. But one of them has a 0. Okay. An additional 0. What will be the closed loop transfer function? I put this in a unity gain feedback loop. So what will be closed loop transfer functions in these two cases? They will be the same. There will be no difference at all. So clearly for the black one, this is the case. For the blue one, also it is this. There is absolutely no difference. How come? I mean, the L is different, right, in reality. So what is different about the two? Yeah, that's correct. But let's say this frequency is omega naught. Okay. So this actually is 1 over 1 plus S by omega naught. This will also be 1 over 1 plus S by omega naught. How many poles are in this black one? The loop gain. How many poles are in the loop gain? 1. There is 1 pole at origin. How many are in this? 2. So how many poles must be there in the closed loop response? 2. So where is it? But logically also the argument that I gave before is right. When the magnitude of loop gain is much more than 1, the gain is approximately 1. So where is what happened to the second pole? What happens is there is what is known as a pole 0 doublet. Okay. So at the location of the 0 of the loop gain, you will have, I forget whether the 0 comes before the pole or after it, but they will be very close to each other. So when you plot only the magnitude, you don't see it. Okay. It looks more or less like a first order system, but in reality this will be this times 1 plus S by Z by 1 plus S by P, where Z and P are very close to each other, but they are not exactly the same. Okay. So you will have a pole 0 doublet. So this pole 0 pair that occur very close to each other because of some particular reason, for instance the 0 in the loop gain is known as a doublet. So that's just additional information, but as far as the magnitude is concerned, it is fair to approximate it by unity up to this point and then with the loop gain afterwards. Okay. Okay, fine. This is the red curve here is L by 1 plus L. So what is phi out by phi ref? So it is multiplied by n, so it simply rises up. Okay. So this is, in the dV case, this is just 20 log n. Okay. This is the magnitude of phi out by phi ref. And it has a DC gain of n, that we already have discussed what that means. If you have, if you delay the input by a certain amount, the output will get delayed by the same amount, which corresponds to n times larger phase when compared to the smaller period at the output. Okay. Also, it says that the output frequency is n times the input frequency. Okay, so that was pretty simple. So if the bottom line is, this is the bandwidth of the PLL. Okay. Now, when we use our charge pump with a current ICP and a resistor and a capacitor, what is this going to be? So, I use our usual system that the output of I use a PFD, the 3-state phase detector. Okay. So, this is my phase detector plus loop filter. So, what is the bandwidth in this case? I mean, the only thing we need to know is KPD, right? The other two are outside. ICPR by 2 pi. So this is the bandwidth. The only thing to keep in mind with something that can cause confusion is, this is the bandwidth in radians per second, where kVCO is actually in hertz per volt. Okay. So it just comes out that way. That's all. And this is in radians per second. So you can adjust depending on the bandwidth, you will have some settling time. Okay. Roughly speaking, it's a first order system with this bandwidth. So the settling time, it follows a first order exponential type of settling with this frequency. Okay. So if you have to design the VCO to settle within a given, if you have to design the frequency synthesizer to settle within a given amount of time, you will have to take care that the bandwidth is large enough. Okay. And such a requirement may come about, especially in a radio it will. In a broadband communication system it may not, because usually you don't have multiple channels which you have to switch. But when you have a radio like a GSM radio, so you have firstly different bands for transmit and receive. You use the same synthesizer. Now for some time you are transmitting, for some time you are receiving. I am not talking about when you are talking. Like actually your speech is digitized and it has separate time slots for transmission and reception. So it switches between transmission and reception. When it does that, it also does it in two separate bands. So it has to, the synthesizer has to switch from one to the other in a given amount of time. Okay. In that case, the bandwidth has to be some certain value. So there are many other reasons. In case of clock and data recovery circuit, it may be the number of bits, number of symbol intervals it needs to acquire the clock. Okay. That is also related to the bandwidth. Okay, next is, let's say the VCO has a phase error. Okay, The output of the VCO is the ideal phase of the VCO plus some error. What is the transfer function from that phi error to phi VCO? I mean, let me not even call it phi VCO, let me call it phi out. What is the transfer function between phi error and phi out? What, qualitatively, what will it be? High pass, low pass, band pass, high pass. Why? Why? Yeah. Okay. Yeah. So when we are evaluating the transfer function between phi error and phi out, we assume that the input is 0, right? So this is 0. Now if this is 0, the feedback will force the output to be 0 at low frequencies. Okay. So whether you put something here or not, the output will be 0 at low frequencies. But at high frequencies, this whole thing is broken. It is like the loop is broken. A very small loop gain means the loop is broken, right? So then phi error simply comes to the output. Okay. So that's what happens. In terms of loop gain, what is the transfer function? What? N by 1 plus L. Is that correct? He says it's N by 1 plus L. What happens at very high frequencies? What is the output? Phi error itself, right? So at very high frequencies, the gain must be 1. Okay. So what is the transfer function? 1 by 1 plus L. Yeah. So I mean, this should be easily recognized as in this form, right? You have L here, the input is here, and the output is here. So G over 1 plus GH, where G is 1 and H is L. Okay. So phi out by phi error from the VCO is 1 by 1 plus L. And this is the reciprocal of L roughly when L is much greater than 1, and it is 1 when L is much less than 1. Okay. So you get 1 over L in the denominator of every one of these expressions. That is the nature of a feedback system. Of course, you can put this entire expression for L into this and calculate it. I am just trying to do it graphically rather quickly. Okay. So graphically, what is it? What is it going to be? I want to sketch phi out by phi error, and I have sketched the magnitude of the loop gain. So from this, I want to get that. What will I get? So obviously you use this to do that. So what am I going to get? So whatever part is above 1, when L is much greater than 1, I said it's 1 by L. So I should make the mirror image of the parts that are above 1, and when it's below 1, I just draw 1. Okay. This is not specific to a VCO. Any feedback system you have, you can do the same. But all of this Bode plot stuff is most useful when you have real poles and zeros. Okay. When you have complex poles, Bode plot as it is not very useful, because when you have complex poles, you can get peaking and so on. That cannot be represented on a Bode plot. So in this part, it is 1, and here it goes up at 20 dB per decade, and here it goes up at 40 dB per decade. So what does this mean? Any error from the VCO, any phase error from the VCO, its low frequencies are suppressed very well. So in a way, if you have a noisy VCO, you can improve its quality by using a phase lock loop. So a noisy VCO means that it has some phase errors, and the phase error has a certain spectral density. And we have not seen it yet, and we won't show it, but it turns out that the spectral density of the VCO phase error is maximum at low frequencies. Okay. The VCO's phase error itself has a low pass type of behavior. So you pass it through a high pass transfer function to limit a lot of the, eliminate a lot of the phase error from the VCO. Okay. Now finally, if I add an error here, what do I get? How will I evaluate that? Huh? Oh, that part divided by 1 plus loop gain. Yeah, that's correct. So what does it look like? So, again you can write the classic feedback block diagram with this part being the forward path gain G and the loop gain being GH. Okay. So what does it look like? Will it look like a low pass, band pass, something else? So we've already finished low pass and high pass, so we can say band pass, right? Low pass. You're a contrarian. Why do you say it is low pass? Can we get it from already things that we have already evaluated? So we know what happens if you add an error here. Can you figure out what happens if you add an error here? It's just divided by the scaling factor, right? So adding this multiplied by this whole thing gets added here. That's the net effect. So I know the transfer function between this and this, I divide it by this transfer function. So what does that look like? Band pass. So I'll say error in the control voltage. Okay. Basically, this is the control voltage of the VCO, but I'll say this is the thing. So times S by P3 2 pi KVCO by S. Is this correct? And this I know what it is, right? So what I need is phi out by phi error control, which is phi out by phi error VCO times this times, okay. Huh? What's that? Which one? 1 over S plus P3. No, this is correct. I don't know if I said it ulta when I described it verbally, but you have to multiply it by that much. Okay. So what does this look like? We just have to multiply it, right? I mean, we have this, and you have to multiply it by this much. Okay? Huh? Yeah, it is more or less a band pass, meaning it is 0 at DC and 0 at infinity, and in the middle it rises up to some value. It is a band pass transfer function. So we have to multiply this with 2 pi kVCO by S, which is an integrator, and a second pole. Okay. So the net transfer function will be, here the slope changes to looks like this. Okay. So I simply add up the two curves on the log scale. So this part is 1 over S by P3, 2 pi kVCO by S. This is P3, and this is phi out by the error from the VCO. Okay. So this is phi out by the error from the control voltage that's added before the loop filter, before the additional third pole filter. Okay. And you can evaluate it from other points also, it looks more or less the same. So roughly speaking, it is low pass from the input to the output. So if you have a noisy oscillator and you want to clean up its noise, you should use a low bandwidth PLL. Okay. The PLL is used in two ways. So it can be used with an accurate, very low noise crystal reference to generate a variable frequency, in which case you use an oscillator, and any oscillator you make is likely to be much more noisy than the crystal oscillator. Okay. So in this case, you are using a clean input and you are trying to clean up the noise of the VCO. In that case, you use a wide bandwidth. Okay. Wide bandwidth means that this low pass transfer function moves out and this high pass corner also moves out. Okay. So the VCO, more of the VCO's error will get filtered out. Now occasionally you also use it to, you have a noisy oscillator and you have a cleaner oscillator in the phase log loop. So you can clean up the noisy oscillator using this clean oscillator. In that case, you use a very low bandwidth so that it doesn't track the input noise of the input oscillator, but it tracks the noise of the VCO inside the PLL. Okay. So it's all just to do with which one has more noise. Okay. From the reference to the output, it is low pass, and from the VCO to the output, it is high pass. Now if the VCO gives more noise, then you use this, and then the reference transfer function will move to this value. Okay. On the other hand, if the input has a lot of noise, you limit the bandwidth as much as possible, so that the transfer function from the input to the output removes a lot of the noise. Okay. And this also helps you. You have to calculate the output phase error, which gives you phase noise. We didn't get into a detailed discussion of phase noise, but while discussing frequency and phase, I had described the phase of an ideal oscillator to be an ideal ramp, and you have deviations from this. Okay. Now, just like any other noise, the RMS value of this noise is what you use to characterize the amount of noise. So this is phase. So this noise is known as phase noise. Okay. Now, in a phase log loop, given the phase noise of the input and the phase noise of the VCO and maybe noise in other components, you can calculate the phase noise of the output by using all these transfer functions. Okay. It's a linear system, so it has some contribution from the input, some from the VCO, some from the internal components. You sum everything up and you finally compute the phase noise. Okay. And finally, the this is the noise from the loop filter. For instance, in the loop filter you use a resistor, and the resistor will have noise. The transfer function from that will be band pass. So ideally what you should do is, in reality what you should do is, you should characterize the noise from every part and then try to minimize the overall contribution. So that's where also you have to play with the bandwidth and the placement of this pole and the zeros and so on. Okay. Any questions on this? Now when you use a CDR with a linear phase detector, you get the similar transfer functions. Again, you evaluate the same thing. Maybe you have a noisy VCO, you calculate the effect of that on the output. Okay. And if it's very noisy, you may have to filter it. Or if the data has a lot of jitter, you may have to filter that by using a low bandwidth, etc., etc. Okay. Any questions? Now this method of, this is not a very complicated method, it's just keeping track of where the poles and zeros are, and if you know how to sketch the magnitude product of L, you should be able to do the rest easily. And when you have more complicated systems than an op-amp, when you have an op-amp or a complicated op-amp, you can use similar techniques to compute the effect of different noise sources and all kinds of things.